Hello, everyone. We are starting a new unit, and it is called Kinetics and Equilibrium. And half of this unit is review for you. We just didn't talk about it in the context of this term kinetics. So this will be a quick unit for you all. Today is May 14th, and you will need Table I handy. I will be referencing that shortly. So let's talk about kinetics today. And today's really a review mini lesson. And in kinetics, we study the rates of reactions. And as a reminder, for collision theory, reactants must collide with sufficient energy and proper orientation in order for a reaction to occur. And this is known as collision theory. When chemical reactions occur, bonds are broken and then new bonds are reformed. And there's a new mixture of products that result. Okay, there are 6 factors impacting the rates of reaction. And be aware that these factors must change the number of collisions in order to impact the rate of reaction. So first, we look at the nature of reactants. Generally speaking, covalent compounds react slower than ionic compounds. And that is because covalent compounds tend to be much larger, or can be much larger than ionic compounds, and therefore there are more bonds that need to be broken and reformed, and so that would impact the rate of reaction. Another factor impacting the rate of reaction is concentration. If you increase the concentration of reactants, they're going to collide more frequently because there's a greater concentration, and therefore we would increase the rate of reaction. Surface area will impact the rate of reaction. The higher the surface area, guess what? There's more space for a reaction to occur on. You're going to have a greater reaction rate. Okay? Pressure can impact some reaction rates, but only involving gases. So as a reminder, right, we have our little particle diagram with gases that are in an uncondensed state. If we reduce the volume of that container, we will push those particles closer together, and they're already in high kinetic energy. They're going to collide more frequently. So higher pressure means higher reaction rates. And that only applies to gaseous systems. If there is a substance that is a catalyst, this will serve to increase the rate of reaction, and it does so by lowering the activation energy. You can kind of think of catalysts as being like spectators at a sporting event or musical event. The point of spectators is to cheer on the athletes or the performers, and that cheering on makes them perform better without the spectators becoming part of the show or part of the event. And finally, number 6, temperature impacts the rate of reaction. which should make sense because temperature is the average kinetic energy of a system. If we increase kinetic energy or increase temperature, we're going to increase collisions and increase the reaction rate. I now have table I out. I'll reference that shortly. And here we go with an example of a potential energy diagram. I hope this looks familiar to you, and this will be a good review for you. So on the y-axis, we have potential energy. On the x-axis, it could be written forward path or reaction. The reaction is occurring over some period of time. We have here on the left, we have two reactants, in this case, glucose and oxygen. Two reactants are on the left. And on the right here, I have two products. In this case, carbon dioxide and water. And you will see that there's a difference in the potential energy of the reactants and products. The reactants have a higher potential energy than the products. So that means a certain amount of energy has been released. There is a release of energy in this forward reaction. Do you recall what kind of reaction this would be? I hope you just said exothermic. This is an exothermic reaction because there is a loss of heat as a result of that reaction. In fact, it's that much heat lost. Now, you may have numerical values here in some potential energy diagrams. And if you do, you would actually be able to indicate the amount of heat lost or the difference. And by the way, that heat released is delta H, the change in heat. And we have lots of examples here in table I. But before I go to that, let me address further this potential energy diagram. Okay, so we've got this reactants. If they possess sufficient energy and proper orientation, they will collide through collision theory, and they will collide effectively enough to produce these products. Well, this amount of energy right here, to the top of the curve, is the activation energy for the forward reaction. This is how much energy is required for that forward reaction. At the very top here, I have a little star. This is called the activated complex. This is where we're in between reactants and products. Bonds are starting to break and new bonds are starting to form, and you have to get past that to complete that reaction. Now we have in red here, this line labeled the activation energy for the reverse reaction. Please be aware, there could be questions addressing the reverse reaction. And that means, carbon dioxide and water reacting and achieving the activated complex and forming their products in the reverse. Okay, and it would require that much energy for the reverse reaction. Okay, now to make this exothermic reaction look simpler, I could just say A plus B reacts to yield C plus D plus heat, because heat is lost, and I'm going to write that on the right-hand side of that reaction because it's an exothermic reaction. And this particular reaction is found in table I, and here it is. Here is our glucose and oxygen react to make carbon dioxide and water. And you will notice that there is negative 2804 kilojoules of heat released. That is the loss of that amount of heat. So table I is very important. The other thing to remind you, not that you can read this in this video, but the delta H with a minus sign indicates an exothermic reaction. So they're giving you some hints there. Every delta H with a negative sign would have this shape potential energy diagram. Now, we mentioned a little earlier in this lesson that catalysts can impact the rate of reaction. If I added some catalyst, I would write that above this arrow. I don't want to write it as a reactant, and I certainly don't want to write it as a product. It is some kind of chemical, and that chemical serves to cheer on the reaction here to create those products. And to draw that catalyst, I would draw that impact like so. So the dotted lines would be a catalyst. What a catalyst would do, it lowers the activation energy required for that reaction to go forward. Let's look at the potential energy diagram for an endothermic reaction. And we know this is an endothermic reaction because we're starting with a certain amount of potential energy with the reactants, and this amount of energy had to be absorbed to create those products. Energy absorbed. Okay, now I don't have a specific example here, but any endothermic reaction is going to have a positive value for its delta H, and we have lots of examples here, and I could use N2 plus 2O2 yields 2NO2, and this would be plus 66.4 kilojoules of heat. The energy of activation for the forward reaction is here in orange. The activated complex is that green star. The energy of activation for the reverse reaction would be in green there, and that difference in potential energy between reactants and products is delta H. It's the heat of reaction, and in this case, it's a positive value. To make this simpler, I could just write A plus B yields, in this case, there's only one product, so I'll just say C. But energy needed to be absorbed. So heat plus A plus B yields C. Could this be energy? Just written, the word energy? Yes, heat is a form of energy. And the amount of energy in this example is plus 66.4 kilojoules of heat. If I added a catalyst, again, what do? You lower the activation energy required, and that reaction will occur faster. And I'm always going to write the catalyst on top of that arrow, because it is like a spectator cheering on this reaction. I hope you enjoyed this mini review lesson. We will start talking about equilibrium next. Have a wonderful day. Bye.